Let us now rewrite the Schrodinger equation in momentum space. The benefits of doing this will become clear in the next couple of videos. So let's get over the chore of doing that in this video. So we'll start with taking the electronic wave function psi of r and assume that it can be expanded using plane waves e power I q dot r. We will assume that these plane waves are a complete set and are orthonormal, and the wave vectors q obey the form that we just discussed in the previous video, that for a reciprocal lattice vector. We can also expand the periodic potential in terms of plane waves, and because the periodic potential has the periodicity of the Bravais lattice, obviously when you expand it in terms of plane waves, it's basically the equivalent of writing the Fourier transform. Then the wave vectors would basically be the reciprocal lattice vectors. It makes sense because if you take the Fourier transform of the reciprocal lattice, you get the if you take the Fourier transform of the Bravais lattice, you get the reciprocal lattice. Therefore, if you take the Fourier transform of any potential which has the periodicity of the Bravais lattice, then it should have the properties of the reciprocal lattice, and therefore it's natural for the wave vectors of the expansion to have just the reciprocal lattice vectors capital K. Now again, this is a complete set and is orthonormal, so you can multiply both sides by e power minus I k dot r and integrate over all space, and you should be able to show this. This is basically how the Fourier coefficients are defined, standard way in which Fourier coefficients are defined. Please pause the video and write these steps down, otherwise it's very difficult for you to understand it. Please take your notebooks as you watch the video, pause the video time to time, write down everything. I'm just following this discussion given in Ashcroft. I'm not changing anything. That's just, again, like I said, for your benefit. You can have a look at there as well, but please write and see, otherwise it's going to escape you. So if the periodic potential is real, and there's a very good choice that it's real, then you can show, given this form for uk, then you can show that u of minus k is just uk star, and if the lattice has got inversion symmetry, then the periodic potential will obey u of r as u of minus r, and then you can in addition show that u minus k is uk equal to uk star, which is just the complex conjugate. So now, given these expansions, we will now insert them into the Schrodinger equation. So the momentum term will just become this. When you take the expansion for the wave function, you will just get that, and the potential will can be written like this. And in the last step, what we have done here is that we have just taken this this k plus q and replaced it by some q prime, and we have just replaced the summation over q with a summation over q prime. Since it's over all values of q prime, it doesn't matter what the index is. So we have just replaced k plus q by q prime. So that would be the full Schrodinger equation. We have also pulled out the e power I q dot r, and here there is a summation over k, and just for future simplicity, we have just replaced that summation over k prime. Again, the same logic, it's all over all reciprocal lattice vectors. It doesn't matter whether it is a summation over k or a k prime. So we just change the index from k to k prime. Now again, because the plane waves are orthonormal, the only way this equation can be can hold true is when each of these coefficients in the curly brackets are 0. You can see that by multiplying both sides by e power minus q dot r, apply the orthonormality, then only one term in the summation will be non-zero, and for that term this equation has to hold. Similarly, for every value of q, the coefficient will be 0. So you get a set of equations for all values of q where this condition has to hold. Now, given this, what we can do is you can take this q, which is a wave vector of the electron, and you reduce it by a reciprocal lattice vector. So you write this wave vector of the electron is equal to some k minus capital K, which is the reciprocal lattice vector. This is done to ensure that the new vector k lies within a primitive cell of the reciprocal lattice, and that primitive cell, the first primitive cell of the reciprocal lattice, is basically called the smallest primitive cell of the reciprocal lattice is basically called the first Brillouin zone. And we will assume that this kind of a rewrite will ensure that this wave vector k lies within the first Brillouin zone. We just saw the Wigner side cell of the reciprocal lattice is just called the first Brillouin zone, and we will assume that rewriting this, basically reducing the q to this form to k, make sure it lies within the first Brillouin zone, and therefore you now have this kind of an expression. It's slightly messy, but we'll have to again we'll have to use our trick to change indices and so on. So now again, what we do is, so you insert q is equal to this, and that's what you get, and you change variables by, you have this messy expression in the of reciprocal lattice vectors, capital K prime minus capital K, and you just write it as some k prime, because again this has to be some other reciprocal lattice vector, so you just take it, and you're anyway going to sum over all reciprocal lattice vectors, so it will be included anyway, and then you make a change of variables, and that's what you get. So again, please pause the video, write it down and see, otherwise again I keep saying it's going to be very difficult for you to understand. Again, it will be difficult for you to answer my questions in the quiz. Now you have this expression, and all values of this small k lie within the primitive cell, that is within the first Brillouin zone. First Brillouin zone is nothing but a primitive cell in the reciprocal lattice. Now please recall that we saw in the previous video that the number of allowed wave vectors in the primitive cell of the reciprocal lattice is nothing but the number of primitive cells in the real crystal, or it is nothing but the number of lattice sites in the real crystal. So you have, if the crystal has got n lattice sites, you will have n allowed values of k in the primitive cell of the reciprocal lattice, which we will call as the first Brillouin zone. From now on, we'll just call it the first Brillouin zone. So now you have n Schrodinger equations for every value, allowed value of k within the first Brillouin zone. So for every lattice site, you have one Schrodinger equation given by this. So for every lattice site, there is a corresponding allowed wave vector. That allowed wave vector is inside the first Brillouin zone, and for every such allowed wave vector, you have this Schrodinger equation written in the momentum space. Now, given this expression, you now see for every value of small k, you have these c's, ck minus reciprocal lattice vectors, capital K prime, capital double prime, and so on. You have such a set. So what you can do is you can take this expression for the wave function that we wrote, and basically change this q to k minus capital K, and instead of summing over q, you can do a sum over this capital K, because for a given value of k, only the capital K's are going to change from k to k prime to k double prime. So you can rewrite the summation in terms, instead of over the wave vectors q, you can keep the wave vector k constant and sum it over all other reciprocal lattice vectors by switching from q to small k minus capital K. And given this, and I can now write this, obviously this wave function will depend on position, so I write as psi k of r. I can pull out this e power I k dot r outside, because this is a small k dot small r, and that's not going to get summed over. So you can pull this out and you have this function. Now remember the form of the block wave function. We said that for electron in the periodic potential, you can write the wave function as the plane wave times some function u of r which has got the periodicity of the lattice, I can now choose this u of r to be basically this. And I will leave it to you to show that this actually has got the periodicity of the lattice as an exercise. So now we have a formalism where we have these nice Schrodinger equations, and we have this expression of the wave function, which is the block form, which is also, this is another way of writing the block equation. So we have this. So we are now going to apply this and see what we get in the future videos.